Okay, I want to present these 3 topics today. In topic 1, I present one theorem about the convergence rate of functional iteration. Take a review about some key points from the last class. An iteration of this form, where capital F is a function, for the solution of a single equation, we still want to solve a single equation. An iteration of this form is called a functional iteration. Say, for example, Newton's method is a functional iteration. Stephenson's method also a functional iteration. There are many other examples. Review number 2. If capital F at S, its value is S, then S is called a fixed point of capital F. Review number 3. If we can find some number less than 1, positive, non-negative, so then this inequality is true for any x and y from the set S. S is a subset of R. As S is a set of some real numbers. If for any x and y this inequality is true, then we say that capital F is contractive on S, on the set S. Now we turn to present topic 1, a theorem about the convergence rate of a functional iteration. I present this theorem in the last class, but today, now I want to present a proof to the theorem. Topic 1. It is a theorem. Let me make some assumptions. Assume A, capital F is in this set. This notation means capital F is defined on the whole real number line, and also has derivative until order Q. All the derivatives are continuous. C means continuous. B, capital F has a fixed point S, of course, in R. S is a real number. C, and the point S at this fixed point, we have derivative of capital F at S is equal to second derivative at S, and so on. And derivative of order Q minus 1 at S, or are 0, or are zeros. But derivative of order Q at S non-zero. Okay. A, B, C. Okay. Now D. The sequence define by this equation has a limit. Okay, the limit is as k approaches infinity, then xk approaches this physics point S. Now conclusion. Okay. Then the sequence, how fast it converges to the point S, order Q. In other words, k approaches infinity, xk plus 1 minus the limit in absolute value over xk minus s, the power is Q, approaches a non-zero number. The number is 1 over Q factorial times this number, non-zero. Yeah, because the number is non-zero, this limit says that by definition, this sequence, the convergence rate is order Q. The proof of this theorem is not difficult. Use Taylor's theorem. Let me present the proof. Okay, proof. Again, let E means error. EK be xk minus s. Okay. We want to prove this equation. Yeah. We want to prove this limit. The numerator is ek plus 1. Denominator is ek. The power is Q. Now, Taylor expansion. By Taylor's theorem, we have ek plus 1 is equal to xk plus 1 minus s. Xk plus 1 is equal to f of xk. So we have xk. S is assumed to be a physics point, so it is f of s. Now I expand the first term. Let me write the first term as xk minus s plus s. Then this is s plus ek minus f of s. Right? Xk minus s by definition is ek. Now I expand the first term by Taylor's theorem. Okay, by Taylor's theorem, the first term is f of s plus 1 over 1 factorial f derivative at s times ek, then plus 1 over 2 factorial second derivative at s times ek squared, and so on. How many terms? Yeah, the last term is this. F derivative q minus 1 times evaluate at s, then times ek q minus 1. Then plus error term. Error term is 1 over q factorial. F derivative q times then evaluate at some point, say sine k. Okay, this sine depends on k, so sine k times ek q Taylor expansion. Now minus second term minus this term minus f of s. All right, now some cancellations. I can cancel f of s by assumption. Assumption C, derivative until order k q minus 1. All the derivative at s are zeros. So this term is 0. This term 0, and so on. This term also 0. Therefore, we have this equation. Ek plus 1 is equal to 1 over qk f derivative q times evaluate at psi k times ek q. Now, from the final equation, we have here. I move ek q to the left side. We have ek plus 1 over ek q is equal to 1 over q f derivative q times evaluate at psi k. What is psi k? Psi k is between let me see, between this point and s, but this point is xk, so between xk and s. Now, by assumption D says that we assume xk is approaching s. Because xk is approaching s and psi k between xk and s, so psi k also approaches the point s. Now take limit. Take limit on the both sides. K approaches infinity. Usually, we like to use absolute value. Absolute value. This is psi k approaches s. So therefore, the limit is 1 over q factorial absolute value f derivative of order q evaluate at s. So done. This equation is the equation here. Yeah, equation here. So we have proof the theorem. This theorem looks simple, but very powerful in looking for order of some iterative method. Let me show you one example. Say, let me pick Newton's method. Okay. So take a look at one example about how to use this theorem. Example 1. Example 1. Suppose R is a root of this equation. Okay, now, so that two questions. If derivative at R non-zero, second derivative at R non-zero, then the Newton's iteration or Newton's method has order 2 of convergence. When the Newton's method is used to find this root R. Okay. Let me answer this question first. Then second question. Okay. Okay. I use the theorem I just presented. Let me see. Newton's method is a functional iteration method. Okay. Newton's method is a functional iteration method. Capital F. Where capital F is recall the Newton iteration formula. It is a xk minus f of xk over f derivative at xk. So capital F is x minus, in the theorem, I want to use this theorem. In this theorem, we need to have a physics point, right? A physics point. Physics point of capital F. It turns out that R is a physics point of this capital F. How? Okay, R is a root of this equation and also a physics point of this capital F. Is a physics point of this capital F. Yeah, this capital F. How to see? Plug in R in this capital F. Then I get R minus F R. But F of R is 0. And first derivative of little f at R we assume non-zero. So 0 over non-zero, 0. So this is a R. So R is a root of this equation, and it is a physics point of capital F. Okay, now there are some assumptions in the field. Of course, we assume capital F is in CQ. We need to have a check assumption C. Derivative at the physics point is 0 until Q minus 1, then Q non-zero. Okay, now let me compare derivative. Take derivative on this capital F, then derivative is this 1 minus x derivative is 1. Then to compute this derivative, closure rule. F derivative times F derivative minus F x, F second derivative x, then all divided by denominator square, F derivative square, closure rule, and then common denominator, then I can cancel this term here. We get Fx, F derivative square. Now, first derivative. Let me see whether or not first derivative at the physics point 0. At point arrow, arrow is a physics point. Now, I plug in. This implies that F derivative at arrow is 0 because F of arrow is 0. Yeah, this guy is 0. So first derivative is 0. Now, let me have a check. Second derivative at arrow is 0 or not. I have compiled first derivative, take derivative again on this quotient. Second derivative is equal to square Fx plus a minus times 2 F first derivative times second derivative, and then all divided by denominator square. It is the power is 4. Power is 4. Now I plug in arrow in x. I want to see whether the second derivative at the physics point arrow is 0. Plug in arrow in x. I can see that, yeah, this guy is 0. Arrow is a root of the equation f of x is equal to 0. So this term is 0. And also here, this guy is 0. So this term, this whole term is 0. So second derivative at arrow is equal to f second derivative arrow. Yeah, that's it. All right. Only this, no, this term is 0. Only this term left. But f derivative, the power is 2. And also there is a f derivative. So the bottom is a f derivative, power is 4. So I can cancel 3 f derivative to get this. Let me go back to the question. The question says that little f derivative at arrow non-zero, second derivative non-zero. That means that this is a non-zero. So the previous theorem guarantees. Okay, if the sequence obtained by the Newton's method, okay, obtained by the Newton's method, is convergent, is convergent to R. Yeah, we need to make this assumption because recall that some starting point, the resulting Newton sequence may not converge to a root. So we assume the sequence obtained by the Newton's method is converging to R, this root. Then by theorem, the previous theorem, xk plus 1 minus this root in absolute value over xk minus R squared is equal to a non-zero number. It is equal to, yeah, this number. 1 over q factorial. Now q is 2. So this is a 1 over 2 factorial. Capital F second derivative at R. It is this number. It is this number. Yeah, this number is non-zero by assumption. So therefore, when first derivative non-zero, second derivative non-zero, then Newton's method is order 2. Order 2. Yeah. Part B. Part B. This is part A. Part A. Now, part B. If first derivative non-zero, second derivative at R is 0, then the Newton's method has order of convergence greater than 2, greater than 2. Okay, when it is used to find this root. To find some other root, I don't know, but to find this root, because at this root, little f has these two conditions, then guarantee if Newton's method converge to this root, how fast? The order greater than 2. Now, proof. A solution. Okay, solution. From part A, we saw that this is from part A. We saw that capital F at R, derivative at R is equal to F R, then over square. Okay. But this guy is 0. R is a root. But the denominator non-zero. Yeah, the assumption is here, non-zero. So first derivative is 0. Guarantee. Okay. Now second derivative at R. We have computed second derivative at R. It is from part A. F second derivative R over F first derivative at R. Now, second derivative here is assumed to be 0. Denominator assumed to be non-zero. So 0. And now continue to take derivative on this capital R. Capital R capital F, the derivative at R. I don't know. Maybe 0. I don't know. Okay. Take derivative 4 times at R. Maybe 0. I don't know. Okay. Continue. At least there must be some integer. Okay. Yeah. Take derivative Q times at R. 0. But take derivative Q times and then evaluate at R. It's non-zero. They must exist such a Q, right? Okay. So therefore, by theorem, xk plus 1 minus R absolute value over xk minus R, order Q, k approaches infinity, is equal to a non-zero number. Non-zero. Okay, where I'm sure Q greater than 2, right? Q greater than 2 because first derivative is 0, second derivative is 0. So Q greater than 2. In other words, if at this root R, at other root, I don't know, if at this root R, these two conditions are satisfied, then if Newton's method is convergent to this root, then the convergence rate at least order 3 greater than 2. Yeah. So done. Actually, this theorem, this theorem is powerful in determining the convergence order for functional iteration method. Okay. Newton's method is one example. There are many other examples. For other examples, you can also use this theorem to determine the convergence order. Very powerful. This is topic 1. Second topic, return to section 3. Section 6, continuation method. Okay. Section topic number 2. Topic number 2, right? Topic number 2, yes. Section 6, continuation method. All right, now this time, we consider the solution of a system of equations. Yeah. We want to solve this vector equation where a vector F is suppose it has n entries. The first entry is a function f1. The unknown also xn. N unknowns, n equations. Suppose. The right side, 0 is a vector. It has n entries. We have a system of equations. We want to use the Newton's method to solve it. Okay, we want to use the Newton's method. To solve. How about let me give a name to this equation. Let me call it 1. To solve 1. But Newton's method has some drawbacks. One is the starting point should be close to the root that we want to find. Otherwise, no guarantee Newton's method will converge. Okay. One drawback. Okay, of Newton's method is the starting point should be close to the root that we want to find. Otherwise, no guarantee. In general, how to know? Because we don't know the root R. Even we have a starting point x0, we don't know whether or not x0 is close to R. In general, this is very difficult. Now, continuation method provide a solution to overcome this difficulty. Yeah, this method says that it doesn't matter if you use my method, you can arbitrarily pick a point as a starting point for the Newton method. Guarantee from the starting point you can get a root of the equation 1. Okay. Now let me present the idea behind this method. Okay. Yeah. All right. Let me write this down. Continuation method overcomes is difficulty. Okay. Okay. The idea. What is the idea behind? Okay. Number one, ideas. Let me write this down. Okay. Embed. The idea is to embed the given equation. Number one, yeah, we are given this equation and we want to solve this equation. Embed this equation in a one parameter family of problems. Yeah, this is one problem. Embed this problem into a one parameter family of problems or equations. Okay. Okay, problems. Let me use problems here. All right. Which problem? The following problem. Okay. Yeah. Parameter. Now parameter is t. Then the problem, the function from equation 1 is f L x L. Then plus 1 minus t. T is a scalar, a number, parameter, times g L x is equal to 0. What is g? Given by us, given by the user, given by the person who wants to solve this equation. How about t? The range for t is between 0 and 1. T is between 0 and 1. Now, the original problem actually is just a subproblem of this equation. Yeah, equation 1 is just a sub-equation of this equation. Why? Yeah, when t is 1, look at this equation. When t is 1, this equation, let me give a name. Call this equation 2. When t is 1, equation 2 is equation 1. Do you agree? When t is 1, 1 minus 1, 0. So the second term is gone. Right? So this equation 2, number 2, actually is equation 1. So equation 1 is just a sub-equation of equation 2. Equation 2 has infinitely many equations because of t arbitrary between 0 and 1. All right. Then how about the other extreme case? When t is when t is 0, when t is 0, okay, plug in 0 in t, then equation 2 is t is 0, first term is gone, second term is g of x. Yeah. What is it? What is g? Given by us. Okay. This equation g is equal to 0. This equation, because of g given by us, we know a root for this equation. Okay. Yeah. Right. About this equation, we know its root. We know its root. Okay. This is A. Now, next step. Okay. Next step. We have a family of equations. Let me copy that family. T between 0 and 1. Okay, now cut the interval 0 to 1. Okay, into subintervals. Okay. Then select points T0, T1, T2, and Tm, so that T0 is equal to 0. When T is 0, this equation is the original equation. Less than T1, less than T2, and so on. How about Tm? Tm is the right side, 1. Okay. Cut the interval 0 to 1 into introduce some points between 0 and 1. Then this equation 2, recall that I call this equation 2. Then 2 has m plus 1, actually m plus 1 equations. When t is 0, when plug in T0 in T, T0 is 0. So the first equation, plug in T1 in T, second equation. G. Plug in T2 in T, third equation. And so on. Plug plug in T m minus 1. M minus 1. Then finally, plug in Tm. Tm is 1 in T. Then we get T is 1. So T is 1. So the second term is 0. So it's 0. Yeah. The final equation is the original problem that we want to solve. Okay. Now, now we start with the first equation. Because G, suppose is given by us. We know the root of G. Suppose, okay, x0. We know x0. If T1, if these points are close to each other enough, and assume this function is continuous in T and in X. When these partition points are close enough, so we can imagine that the root of the first equation and the root of the second equation, they're close. So if I have a root for the first equation, I can use the root as the starting point for the second equation by Newton method. After I found the root of second equation, I can use the root as the starting point to determine the root of the third equation by the Newton method. And so on, and so on. So the second last equation, after I get the solution of the second last equation, the solution should be close to the solution of the final equation. So I use the solution of this equation as the starting point by Newton method to solve the final equation. The final equation is this problem, this equation given to us. This is the idea of continuation method to overcome this difficulty. The Newton's method requires starting point is close to the root. Okay, otherwise, no guarantee Newton's method will converge. Now, this method overcome the difficulty. You can starting with arbitrary point, but still can make Newton's method works. For some other details about this method, I present them in the next class.